For about a century now, we've pictured black holes as these super dense points that literally bend the fabric of space-time. It's a powerful image, right? But what if that's not the whole story? What if the reality of what's going on is built on something completely different?
You see, here's the thing. At the very heart of a black hole, according to our current theories, our math just breaks. We get an infinity, a singularity, and in physics, an infinity is usually a giant red flag telling us our theory's missing something. So a pretty radical new idea, called dynamic vacuum field theory, or DVFT for short, asks this exact question. It says, hey, maybe space-time isn't the fundamental backdrop of the universe. Maybe it's just an emergent effect of something way, way deeper.
To even begin to wrap our heads around this, we have to rethink the most basic thing we can imagine, empty space. Because DVFT says the vacuum isn't a void at all. Nope, it's a physical, dynamic medium.
And this table just lays out the shift perfectly. In Einstein's general relativity, the vacuum is nothing. Space-time is the stage, and gravity is just what happens when mass bends or warps that stage. DVFT completely flips that on its head. It says the vacuum is a physical field. Space-time is just what we perceive as things move through that field. And gravity? It's not a bend, it's a distortion. Think of it more like a current or a flow within the vacuum itself.
So, to put it simply, DVFT is a model where the vacuum is a real, tangible thing, and everything we call gravity, seriously, from an apple falling from a tree to entire galaxies orbiting each other, is just a result of how this medium behaves.
Okay, this immediately leads to a huge question. If you don't have infinitely bent space-time, how in the world do you build a black hole? How do you trap something so perfectly that not even light, the fastest thing in the universe, can escape?
Well, the answer is an idea called causal trapping. In this model, a black hole is a spot where this vacuum field is flowing inwards, kind of like water going down a drain. At a certain point, this inward current actually gets faster than the speed of light. So anything that crosses that boundary, light included, is just swept along for the ride with absolutely no way to escape.
Here's a great way to picture it. Imagine you're a swimmer in a really fast river. You've got a top swimming speed, right? Now up ahead is a massive waterfall, and the closer you get, the faster the river flows. The event horizon is that precise point of no return, where the water is flowing downstream faster than your absolute top speed. It doesn't matter how hard you swim against it, you're going over the edge.
So you might be wondering, what keeps this flow from, pushing things away sometimes? Why is it always an attractive force? Well, the theory has a rule baked right into it called vacuum null positivity. Basically, it's a law that says the energy of this vacuum field can never be negative. And it's this fundamental positivity that drives the inward attractive flow that you and I experience as gravity. Okay, so we've got our cosmic drain, but we know that real black holes in the universe spin, and they can spin incredibly fast. So how does a drain in the vacuum start to rotate? How does that work? How do you get this fluid-like vacuum to spin in a way that actually matches what we observe with real, spinning black holes out there in the cosmos?
Well, the process basically happens in 3 steps. First, the vacuum field develops a circulation. Just think of stirring a cup of coffee and creating a little whirlpool. Second, that spinning motion creates a real, tangible current of momentum within the vacuum. And third, and this is the amazing part, this swirling vacuum current literally grabs onto the emergent spacetime and drags it along for the ride. And that is DVFT's explanation for the famous frame-dragging effect, where a spinning object twists the spacetime around it. And get this isn't just some wild guess. The theory actually shows how the frame-dragging effect we've observed around spinning black holes emerges naturally from the behavior of this vacuum vortex. It's a huge predictive point for the model.
Now, let's talk about one of the coolest and craziest ideas in all of physics, pulling energy out of a black hole. In this new picture, you're not stealing energy from some mysterious singularity, you're tapping into the unbelievable power stored in that cosmic whirlpool of the vacuum. All right, first up we have the legendary Penrose process. In this model, you send a particle into that spinning region of the vacuum. If you can get it to split in just the right way, one piece falls in, basically giving its energy to the rotating vacuum. In return, the other piece gets shot out with even more energy than the original particle had to begin with.
The second method is called superradiance. It's kind of like throwing a special kind of pebble into a spinning pond.
If you send a wave with just the right frequency at this spinning vacuum vortex, it doesn't just bounce off, it comes back stronger, amplified. That extra energy has been snatched directly from the rotational energy of the vacuum field.
So, the big takeaway here is that both of these really exotic ways of getting energy are reframed. They're no longer abstract mathematical tricks, they're tangible ways of interacting with a physical, rotating medium. You're literally tapping into the raw power of the spinning vacuum.
So what's the big picture here? If a theory like this holds water, it could seriously reshape how we understand some of the most fundamental laws of the entire universe.
What's really fascinating is how this all connects to thermodynamics. When you start to include quantum effects, DVFT actually predicts a version of the generalized second law. It suggests that a black hole's surface area is directly related to its entropy, its disorder. And that creates this beautiful, elegant bridge between the most massive objects in the cosmos and the basic rules of heat and chaos.
And that brings us to our final and maybe most mind-bending thought. For decades, there's been an idea in physics called the no-hair theorem. It basically says black holes are simple. All you can know about them is their mass, their charge, and their spin. They have no other unique features. No hair. But if a black hole is actually a complex swirling structure in a dynamic vacuum field, could it have subtle, unique features, little imprints from the vacuum's own properties? Could this theory finally reveal hair on black holes, and in doing so challenge one of the biggest ideas in modern physics? Now that is a question this new model leaves us to explore.